All right, we're going to get started. Thanks, everyone. I hope you had a good coffee break. I'm excited to welcome Paul Walton from Trimble to the stage. I've gotten to know Paul the last 2 days, and very excited for the talk here. Paul has been an innovator at Trimble for over 28 years, with 8 patents and a Trimble Innovation Award. This history of embracing cutting-edge technologies is illustrated by his adoption of MongoDB when creating the connected farm platform for the Ag division starting in 2011. Paul has continued to push the envelope with MongoDB in subsequent projects for Trimble IoT services, Edge Analytics, and now for building Constructions Connect and Scale initiatives. He selected MongoDB Atlas Search, and he's here to talk about that. Please welcome Paul Walton.
Thank you. So earlier this year at MongoDB World, I was wandering around the exhibition floor and encountered Justin Lebrec, who was standing on his own. So I approached him and asked him his thoughts on a use case that I was thinking about using the extended reference pattern to solve. He shared his thoughts, and we chatted on various schema-related topics, and he must have repeated the same general advice about at least three times. At the time, I didn't really figure out how to apply the advice to my use case, and was slightly puzzled why he mentioned it so often. This advice obviously stuck in my head, because a week later I woke up at 4 a.m. with an aha moment. Based on his advice, I had an idea to a solution to an ongoing problem that made me revisit a decision I'd considered set in stone. So the theme for this talk is to encourage you to always challenge your assumptions and leave no stone unturned. So today I'm going to provide a little background on Trimble building construction domain and explain why Atlas Search was selected to power our content platform discovery solution. Then I'll share some experiences and learnings from our solution development with Atlas Search, which will segue into our future ideas for innovation with Atlas Search before wrapping up with a summary and hopefully time for questions. So what does Trimble do? Put simply, Trimble is transforming the way the world works. We develop productivity solutions that promote efficiency and sustainability, mainly at the enterprise level. These solutions differentiate at the connection of the digital and physical worlds. For example, enabling planning data to be transferred from the digital office place to the physical work site, then capturing the physical results from the site to be sent back to the digital office to facilitate tracking the physical progress in the digital world. Trimble's strategy is to integrate workflows and stakeholders across industry continuums. The construction industry is one of the core industries served by Trimble, and our division develops applications to support building construction workflows from mechanical, electrical, and plumbing trade disciplines. These applications connect the design, estimation, bid, procurement, and fabrication phases of building construction. Our group is focused on developing platform services that deliver the shared resources required by these building construction solutions. These services reside in the highlighted layers shown on the conceptual view of an industry platform shown on the right-hand side. To deliver these shared resources, we have developed a central library for building components that are normalized to support the workflow consistently across the previously mentioned phases. As you can see from the images, these components have diverse properties, attributes, and purpose. Additionally, they are sourced from hundreds of different manufacturers with different classification and identification schemes. Some components have dimensions, some have specifications, some have properties specific to the manufacturer, and almost all of them have important supplementary information like component pricing and labor rates. This illustration shows the JSON graph view of a typical component. which serves to highlight the variability in properties and capabilities that need to be modeled. To cope with the challenges of component discovery, a JSON-based search engine was required. In order to support our consumers' discoverability requirements for these components, we needed a full-text search capability. As MongoDB is a Trimble preferred technology that is already used in our group, we were excited to hear about how Atlas Search was based on the Lucene search engine, so we decided to choose Atlas Search for our component discovery solution. We started our Atlas journey a couple of years ago now with this simple problem statement for supporting consumers' abilities to search for components. So it was super easy to get started. Well, once we created a search index for the components collection, and remember 2 years ago there was no visual editor capability. So well, we actually needed a little help from MongoDB consulting on how to define the initial index given our complex JSON structure. Then we were back in familiar territory by creating an aggregation pipeline query for our simple text search operation, as you can see here. For the path parameter, we decided we needed to use a wildcard as we wanted to search across multiple indexed component fields so that the consumer did not need to provide any component property information, and we'd keep the search simple, well, at least for the user. Lastly, based on our consumer requirements, we specified some fuzzy options. We guessed at these parameter values based on what seemed to make sense from the documentation. And don't worry, I will talk about this more in a later learning moment. We anticipated the need for pagination support to limit the results returned. As we'd already seen, we could get quite a lot of results from the search queries we used to perform initial testing. But the performance was really poor, a request often taking over a minute. We tried to simply cap the results at 1,000 based on a recommendation, but our consumers wanted to get the item count in order to present it to the user. So we were sort of stuck. And in most situations like this, we headed over to Google Search and soon discovered that it turned out to be a commonly reported issue due to the sequential interaction between the search and the aggregation processes. Upon further investigation, we discovered the MongoDB user feedback forum site for Atlas Search, and that's pictured here, where features and improvements can be requested and voted up by the community. So I asked the whole team to vote on the improvements so we could see if we could get them prioritized. It sort of worked, because soon we started getting email notifications as the features were considered and their status changed. While we waited for our voting to have an effect, though, we had to address the performance issue in order to make our delivery deadline. Fortunately, we could make some changes to improve performance based on consumers' existing implementation, as we discovered that all the results pages were being loaded into the client so that the components could be sorted and filtered prior to presentation to the user. So we created a solution that cached the search results cursor so that when the next results page was requested, it could be quickly produced using this cached cursor. This approach meant we were not able to provide the total item count as shown here, but so not surprisingly, it turned out the consumer was okay with this, as they were caching all the components in the client application anyway. However, this was a short-term solution as it does not scale and is expensive with resources, so we really needed a solution to the Atlas search feature requests. Thankfully, we received this nice invitation to join the MongoDB DAZZLE program from Marcus Egan. The DAZZLE acronym stands for Driving Atlas Search Advancement and Lifecycle, which, while a very dazzling acronym, does seem a little contrived to me, but more importantly, it gave us early access to these new features. So we eagerly attempted to fix our performance issue. But to our surprise, initial trials with the early release version did not result in the noticeable performance improvements. Our awesome MongoDB account manager arranged a video meeting with Marcus Egan, and thank you, Taylor. We talked about our search use case, and he even sent me a couple of search aggregation queries during the call. during this meeting with Marcus, I soon realized that aggregation facets are not the same as search facets. The queries are shown here, and as you can see, I've highlighted the different facets, which helped our understanding greatly. So, based on these initial queries provided by Marcus, we created an aggregation query that correctly used search facets. And here is our solution. As you can see, it uses the search meta operation using the new count operand with the total type option selected. We followed the MongoDB guidance to use search for the search results and search meta for the metadata results. So we execute the search to get a page of components, and this search meta to return the item count, and we do those concurrently. You can see the performance boost this gave us, as this particular query executes in well under a second. So we have now replaced the cursor cache solution with one that has better performance, provides the total count, and consumes less resources with better scalability. Best of all, we had positive feedback from our consumers, so as they can now do 5 searches in the time it used to take just 1 to complete. We really liked that MongoDB kept us informed at various phases in the development of this new feature. Here's an image of an email I received. You will notice there's a reference to 100 times performance, and based on our data, this is accurate. So after that major success, the next problem was to address how to help the consumers move away from loading all the components into the client application. To do this, we needed to support the filtering in the search query so that the results can be filtered before we've been returned to the client. As we can see here, the compound search operation supports filtering. So we can use this to filter the search results, but we do need to add the required filter fields to the search index for it to have any effect. So the real challenge is how to provide the appropriate filter values to be used for the specific component properties. In Trimble building construction, our client applications use 2 scenarios to obtain these specific component property filter values. The first scenario is called a drill down classification, which is based on the application's component taxonomy. Here we see the selected discipline is plumbing. From these options, the valves commodity was selected. So this level shows the different valve types available. Now selecting ball valves, for example, will then provide the user the ability to search all the different ball valve components. This classification approach is very linear, and so it doesn't support group selections, and it relies on the taxonomy of the application. Being a content platform that supports multiple applications, we need to be agnostic of these application-specific taxonomies. So our service needs to provide the component property values for a specified property after the filters provided have been applied. These filters will use the values from previous classification filter property value requests, all of which is actually simpler than it sounds when you think of the method as being reentrant. We had already developed a drill down classification for another service based on query operations. The implementation of this service required a separate classification collection to support the classification queries. The collection schema used the attribute pattern with a compound index to support aggregation, match, and then group operations. This did provide a very effective solution for this classification use case. The second scenario provides the property filter values based on an initial search, which can optionally include a filter. Here we see the initial search results are based on an electrical classification, thus providing a filtered result set, and the user now gets to limit the search even further by selecting the specific properties in the property panels on the left. As you can see, the checkboxes in the panels on the left allow the support for grouping selections. This scenario, so our service needs to provide these component property values and counts for these panels based on the specified search and text filters. So this scenario seems to be exactly what search facets were intended to support. So we were very excited to add search facets to our index using the same classification attributes as before, plus it seemed like the search facets could be applied to both property filter scenarios, thus reducing our resource usage. However, the addition of search facets highlighted a limitation with our classification schema. While the attribute pattern worked well for classification grouping to provide filter values, it did not provide the resolution required for the buckets for the specific filter attribute like material. Instead, highlighted on the left, we are limited to indexing the value field, which results in all the values being mixed in the attribute buckets. As you can see in the illustration on the right, it means that shape attribute values like round are included in the buckets along with all the other attribute values and not just the material values. This situation is exacerbated when more attributes exist in the array. As it increases the mixing in the buckets and without the name context in the buckets, it's difficult to figure out what the attribute associated with the value ID is actually. And this makes the results pretty much next to useless for our purposes. So it just so happened that around this time I attended the Atlas search workshop at MongoDB World with Karen Urolme. This workshop provided some excellent search results like this What's Cooking site, which interactively illustrates search facets. And if you'd attended Karen's talk this morning, you'd see she's taken this one step further with a World Cup selection, team selection application. But for us, we use this site to learn about search facet indexing, using search meta for property filters, and searching with facet filtering. With this learning, we decided to replace the attribute pattern with a simple flattened document. Then we were able to create a facet index for each document property as shown on the left, which then enabled us to use facet buckets based on a specific attribute when specified in the search facets query. Now, as you can see on the illustration, only the material values are included in the buckets and they are very easy to consume. Now, with search facets, we can support both filtering scenarios using a single collection and search index. These filter endpoints are represented by 1 and 3 on the diagram, but it should be noted that the $sort comes with a MongoDB performance warning. So based on our research, we plan to research this sort with the new sort array operation to boost performance when we migrate to version 6. To provide the component results pages shown by 2 in the diagram, we leveraged our existing implementation presented earlier that uses search and search meta queries concurrently. So our solution performs really well, is easier to maintain while requiring fewer resources. But wait, there's actually more. We also discovered an opportunity to improve our performance further with another Atlas search feature called stored fields. Based on some investigation, we discovered we could use the stored field feature in the search index to store the primary keys shown on the left. Then in the aggregation query, we include the return stored source option in the search query shown on the top right, so that it simply returns the stored primary keys to the next stage of the aggregation pipeline. As we learned earlier, this is a sequential transfer, so limiting the data passed from search to the aggregation processes improves performance. The next stage then applies the pagination using skip and limit to only return the primary keys for the component page. Sorry, I excluded these to make it all fit on the page. The last stage in aggregation is to merge these IDs with the component entities using the $lookup. This gave us a performance boost for returning pages with consistent response times across the complete results set. With this solution, we were very happy with the performance and capabilities that the new Atlas Search features has provided for our solution. But we soon discovered the search results were not always what the consumers expected. For instance, the addition of keywords to the search text resulted in more diverse results being returned. Consumers wanted the addition of search keywords to provide fewer or more relevant results. Our solution was to split the keyword, the search text into keywords and apply an AND style operator with the keywords. This was done using the compound search with a must clause for each word. And here we see an example using copper pipe. We also went with defaults for fuzzy to simplify the queries and avoid any additional results based on our previously guessed values. This is one of those what were we thinking moments. As in my experience with MongoDB over the years, I've noticed that the default behavior is nearly always the best place to start, and I'm pretty sure I recall in the early days Elliot stating that do the right thing out of the box was one of the core tenets in MongoDB. So I'm not sure why we didn't just use the defaults from the beginning. Anyway, the split text approach did improve the results as it reduced the total search item count from of just over 100,000 to just under 20,000. I am concerned that it may reduce the effectiveness of the search analyzer that is specified in the search index, as we've added custom parsing, and it does increase maintenance efforts as changes require code deployments. Wasn't the only issues. We also received some feedback from consumers who saw issues when searching with catalog numbers. Here is an example reported by one of our consumers where they were searching for an LTA 200-50 catalog number, and they reported lots of irrelevant results. So we reached out to MongoDB Support, and as usual, they were able to identify the issue and provide an actionable solution. The user's issue was caused by how the standard analyzer used to create the index tokens was splitting the text and dropping the hyphen, thus creating lots of partial tokens. In this case, LTA 250. So as you can imagine, 50 could easily cause the component to get included in potentially lots of irrelevant searches. Plus, the more words indexed with hyphens, the more partial tokens are generated. The suggested solution was to create a custom analyzer to keep the text intact in a single token, and this is shown on the right. We also needed to update the search index to use the custom analyzer for the appropriate field index, and this is shown on the left. During the MongoDB World Workshop, Karen also shared a link to this search index's webpage, and she even showed it this morning as well, although I noticed she'd made a few improvements to it. But this web page has a tool to interactively visualize tokens and generated from the different analyzers, and it was hugely educational for us. It's also accompanied with a tutorial titled Analyzing Analyzers to build the right search index for your app, which, as you can gather from the title, is very appropriate to our situation. And we've used both these resources to greatly improve our understanding of analyzer behavior. So while our solution suggestion worked for the specific use case of LTA 200-50 in the search text, we soon noticed other issues, like when only LTA 200 was entered into the search text, we did not see the expected LTA 200-50 included in the results. This led us to study some of the values stored in the component name and category number fields, and these are shown here. As you can see from these samples, the hyphen is not the only special character that needs to be considered. In fact, as you can see, there's quite a few others. It is apparent that we need to be more systematic in how we address the search results quality improvements, making sure that we include the consumer's use cases and data captured from actual search requests. Therefore, we're going to need more innovation in the future with custom analyzers based on a better understanding of the component property fields and how they're being accessed. Other future work includes investigating the effects of the various fuzzy search parameters, which can really help fine-tune the search results, but also require some in-depth understanding and probably should not just be guessed. As I mentioned earlier, migration to version 6 will help us benefit from new search features like sort array and an improved $lookup performance. Our consumers have already begun asking about autocomplete, so I expect we'll be adding this capability to our platform in the future. At MongoDB World, there was a lot of innovation around the Atlas Data Platform concept, which I believe our platform can leverage in the future, can be leveraged by our content platform. Think back to the JSON graph earlier in the presentation and imagine how GraphQL could be used by consumers to specify the JSON they want to receive, and so that they only get the properties they need. We also see Atlas charts as a way to easily visualize our content and its usage to support content management and performance improvements. Plus, we have many more ideas for innovation not captured here. So to summarize, Atlas Search has improved our content platform with the best-in-class building component discovery capabilities. Schema design targeting the workload and access patterns is the path to optimal performance. Appropriate use of analyzers can really improve your search results and can work really well with fuzzy parameters. MongoDB has a great user forum that can help drive the innovation you need from Atlas Search. Lastly, MongoDB Support is a very effective resource for finding actionable solutions to your specific problems. And just my final takeaways from my talk today. It's very easy to make assumptions without even realizing often, so always be prepared to challenge them. Be prepared to pivot your solution when you gain new understanding. Remember, it's not set in stone. And never forget, the point of the solution is to solve the user's problem, so include them in the problem as often as possible. That concludes my talk today. I'd like to thank you all for listening. I think we now have a few minutes for questions. Wow, that took longer than normal, man.
Fantastic. Questions for Paul?
Good.
Yes.
What was the total size of the data you were searching over?
So we have about 800,000 components currently in our database, but the projected upper limit is going to be in the 30 to 50 million. So we've got a long way to go, obviously.
All right, Paul, will you be hanging around a little bit for questions?
Yeah,
All right.
I'll just loiter.
All right, so Paul will be available for questions. Thank you so much, Paul. Another round of applause. Great talk.